We now extend our treatment of cyclic molecules to consider fused ring systems. Our learning goals in this case are going to be the configurations of those systems and where their relative degrees of strain come in. So what are fused ring systems? These are basically cases where we have a molecule with two or more cyclic pieces that are connected together by sharing at least one atom in common. So what are some of the most common varieties? Well, one variety is where they have one atom shared in common, and this might be the common atom that they share, and this atom is attached to two different rings like this. So this is how they are fused together. This almost always involves a carbon atom because you can see it needs to have 4 bonds, 2 to each ring, and because of the tetrahedral geometry around the carbon atom, those 2 rings are going to lie in planes or similarly or approximate planes anyway, that are roughly perpendicular to one another. Because of this shape, these are called spiro compounds. While there's lots of interesting spiro compounds to talk about, we're going to focus most of our attention on the next example, which is 2 atoms shared between the rings. We can also have more than 2 atoms shared, but these represent more complicated cases, and we'll save those for another time. So I'm going to spend the rest of this class anyway, this video, talking about systems where we have 2 atoms shared between fused rings. So when we have 2 fused rings with shared atoms, this means it's not only the atoms but also the bond that connects them that are shared by the 2 rings. These 2 atoms that are shared are almost always carbon atoms. Some examples include the following compounds. These are all drawn in bond line diagrams, and you'll notice that the 2 rings that are fused sometimes are the same size rings as they are in the bicyclo-3,3,0 octane in the middle, or in the decalin compound shown on the far right. But they also can be different sized rings. It doesn't really matter. As long as they have 2 atoms that are shared between them, they fall into this category. Let's look a little bit more at the fusion geometry because this is going to be important in understanding the relative stabilities of these different possibilities. Okay, if I take the 2 carbons that are shared between 2 rings, I'm going to draw them here. I'm going to take one of the positions on the upper carbon and attach a hydrogen to it, but that means the other 2 are the things that are going to connect 2 rings on the other side. Now I'm going to label the 3 positions on the bottom carbon A, B, and C, and when I do this, I'll note that the left-hand side, the yellow side, cannot connect to C, and the right-hand side cannot connect to B because those are on the opposite sides of the molecule. It'd be very difficult to swing a ring around and connect up over there. So when I do connect those rings, when I go from the left-hand side to form ring 1, I can connect it up to either position A or to position B. When I do the same for the right-hand side to form ring 2, I can connect that side to either A or C. If I want to really see what this means, I'm going to view from the bottom. So what I'm going to do is I'm going to take this picture and I'm going to swing it so that the bottom swings out and toward us and the top swings away from us. When I do this, I'll end up with a Newman projection that looks something like this. Okay, notice that the A position now has swung up and it is now sticking straight up. The hydrogen that was on the upper carbon has swung down and it's now pointed straight down. The A and the A position and the hydrogen are in an anti position relative to one another. All right, so now what happens when I draw the possible closures out of the left-hand side to form ring 1? I can either connect it to position A or to position B. When I do the same to form ring 2, I can do that to either position A or to position C. Okay, we can now see why it's restricted to those, because it'd be much harder to swing a cycle around that connects them to the opposite side of the molecule. All right, let's consider the first possibility. I'm going to create ring 1 so that it's connected from the left-hand connector to position B. And then I'm going to connect ring 2 so that it's connected from the right-hand position to position A. Okay, when I do this, I'll get this particular arrangement of the 2 fused rings. Now I could have similarly connected ring 1 so that it connects to A and ring 2 so that it connects to C, and I would get a compound that looks something like this. You'll notice that these 2 compounds are really mirror images of one another, so they'll have similar physical properties, but they are not in fact exactly the same. if you will, they have a handedness to them that prevents them from being overlapped with one another. So they aren't going to be equivalent compounds, but they will have very similar sorts of physical properties. I can also connect my first ring from the left-hand side to B and the right-hand ring, ring 2, from the right-hand side to C. And when I do this, I get this configuration. Now, one thing I want to point out is if I take the positions that are not hooked up in the rings and substitute them with hydrogens, let's look at the difference between these possibilities. The first two show the two hydrogens are basically in a gauche position relative to one another. They both lie on the same side of the fused rings, whereas in the bottom one, the two hydrogens are in an anti-position relative to one another. They are on opposite sides of the fused rings. This actually is an important consequence as it affects the stability of this fused ring system. So let's look at this. The first two that I drew are something that we would call fused in a SIS fusion. The SIS fusion means the two hydrogens are essentially on the same side of the fused rings, and so if I put those rings in now, they're attached here and here. Those two hydrogens on the same side, as I mentioned before, are in a gauche position. Because they're on the same side of the fused rings, that's why we call it a SIS fusion. Now, this in a real molecule like cis bicyclo-4,3,0-nonane, it would look something like this. So let's draw a correlation between our Newman projection on the left-hand side and this real picture. This is the center of the Newman projection, and you can see the two hydrogens that are in that cis or gauche position relative to one another. The four carbons that we've drawn explicitly are these four carbons, and you can see that the two above are attached to ring 1, while the two below are attached to ring 2. All right, so this gives you an idea of what this looks like in a real molecular system. I want to color 3 of these atoms red, though, to make a point, and that is that these 3 atoms are very close to one another, so they're likely to have some amount of steric strain associated with them. This is true in most of these cis fusion fused ring systems, where you're going to have an enhanced degree of steric strain because of this crowding of these atoms in between the two rings that are fused. Well, let's contrast this with transfusion, which will be the case that was the bottom on the previous slide. Okay, this is where the hydrogens are on opposite sides, so they're in a trans position configuration relative to the two rings. They're drawn here. So being on opposite sides, this represents an anti-position in the Newman projection. And if we draw a real molecule that looks like this is the trans bicyclo-4,3,0-nonane related to the first. Now we can see that our Newman projection is centered here in the middle. The two hydrogens that are anti to one another are drawn here, and the various carbons that we've drawn are these 4 carbons here. Now the two rings that are fused are here and here. All right, we can see that there is much less congestion in the middle and therefore much less steric strain involved in this molecule. So what we'll generally find is that for fused ring systems that contain 2 shared carbons, the lower energy one is going to be the one that is a transfusion as opposed to a cis fusion. Now there may be other factors that would favor the cis, but in general you'll see that transfusion will be a little bit lower energy structure.